Okay. All right. Hello, everyone. And thanks, everyone, for joining in the Computer Over Data Working Group. This is our third session. Today, we're very fortunate to have Nilay and Sergey from the Kamu team that are going to give us a deeper dive on their technology stack, and also Al Morris from the Koii Network. We're very excited to have an overview on both of these technologies. And before I do turn it over to Sergey, I do want to just give a brief advertisement that we are in the early stages of scheduling the Compute Over Data Summit to happen in Lisbon. It's going to be around November 2nd or 3rd, so you'll see a lot more communication about that. We want to have everyone in the community involved. Also, ecosystem partners that you care about, your users, potential investors, and those sorts of things. So, so please pencil that in on your dates. And that's the only announcements I have. Sergey and Nilay, I'll hand it over to you guys and let you take us through content on Kamu.
Thank you very much, Wes. We're really excited to share what our team has been working on with the group. So let me just switch over to my laptop and share my screen. All right. So as you might have known, that our focus with the Web3 data, Kamu is focusing on how organizations can rapidly and efficiently exchange the information, and also how they can collaborate together on enriching, improving data, making iterative improvements to it. And all of this should also work in a completely decentralized and a trusted way. So today I'm going to be showing you our tool called Canoe. It's a single binary app that I have installed on my laptop. You can download it and give it a try today. You can think of it roughly as a Git that meets Kubernetes meets blockchain. I know it sounds strange, but by the end of this presentation, I'm sure it's going to make sense. So, sorry, just a second. You start working with Canoe by creating a workspace. So I'm running Canoe init command here, and we can see that our workspace right now is empty, no data sets there. So in this demo, I'm going to be showing you how we can build a very small data pipeline that pulls data from the blockchain, Ethereum blockchain of some random account, and we're going to analyze the market value of their portfolio using Canoe. So I'm going to run Canoe pull command and explain what it does. So basically, we want to make data sharing as easy as possible. So we try to achieve the same simplicity as IPFS brings to sharing files. We do the same, but for structured data. So with this pull command, you can see me pulling information from IPNS subdomain of our website. So this URL basically points to the IPFS CID, and we're actually pulling structured data set from IPFS, and we're just giving it a certain name. So this is what we're pulling is the data on the Ethereum to USD exchange prices that we're in the background, we're constantly ingesting from a 3-tier of cryptocompare.com. So data set is in now. You can see that 44 blocks was downloaded. And if we do Canoe list again, we can see the data set is here. It's a root data set, which I'm going to explain what it means later. And it has around 78,000 records in it. We can immediately jump and start exploring this data set. For example, Canoe tail command is going to give us a sample of last events from this data set. We can also do cool things like run SQL just from the command line. We can even drop into SQL shell and start exploring the data set. But I'm going to show you the other way to explore it is by running Canoe notebook. So this thing is going to start a Jupyter server inside of your workspace and let you explore the data using Jupyter notebooks. So here I have a small notebook prepared for us. First line is just some Python imports for us to be able to visualize the data. Then I'm loading Canoe extension here and importing the data set that we have just ingested. So it takes a bit of... Yeah.
Sorry, I just wanted to add, we have an entire online demo that we will share where you can try this session and others in your browser without downloading the data. We just wanted to add it quickly. Sorry, go on.
Yeah, so it takes a bit of time for the first time because in the background, it actually starts Apache Spark server for you, allowing you to send the SQL queries directly from the notebook and massage the data with Spark before retrieving it into your notebook and visualizing it with Python. Here, I don't have any fancy data processing in SQL. I'm just getting the entire data set into a local variable, and then we can plot it using hvplot in Python. So this is the data set that we just got, as I said, the crypto exchange prices. So moving on from this, you might be wondering, like, what this data set, where is actually coming from, and how did we get it into the system? So I'm going to show you how you add such a root data set to the system. So the data sets in Canoe are all expressed as YAML files. So you're going to get a lot of Kubernetes vibes if you worked with Kubernetes before. Here we're going to look at one of such files that I prepared called account transactions dataset. So there's two types of dataset in a system. Root datasets are non-reproducible source data. So here we see a root dataset, and we are specifying where to get this data from an external source. We're going to be pulling data from Etherscan API, from basically getting the list of transactions of this specific address. Then there's some boring stuff like massaging the data from the JSON format into more typed schema, and we're using Spark SQL engine, one of our plugin engines, to again shape it into better types and rename some columns. So I'm gonna go ahead and do Canoe add datasets account transactions. I'm gonna add this YAML. Immediately we see dataset is here, but currently it's empty. So I'm gonna do Canoe pull command again on the account transactions now, and it's gonna start ingesting the data. So what it's doing here, it downloaded, reached out to the API, downloaded the data. Now it's spawning the Spark engine once again and ingesting the data per specified schema and specified SQL.
And one other thing to, sorry, go ahead.
No, please.
One other thing to note here, I was going to say, you can add any boring like data cleaning steps in this ingest, and you can automatically do this process like repeatedly without ever having to touch the pipeline again. Sorry, go ahead.
No, that's great. So then do you create a hash of the data and the intermediate steps so you know you don't have to do it again?
Yeah, exactly. This is what I want to dive right after this. So as you can see here, if we run Canoe log command on this account transaction dataset, the data is in Canoe is actually ingested in the form of a ledger. So both the data itself is a ledger, but we also have the metadata ledger. So in this ledger of metadata, you can see the first block is a seed block, which assigns the unique, globally unique identity to the dataset in form of a DID. Then we have this block that was defining where to get the data from. We also have vocabulary blocks that defines some names for special columns. You can have licenses, you can have provenance information, you can have governance stuff in it. So this is the metadata format is basically extensible. We want this to be the standard way to propagate any kind of meta information along with data set that is so important to keep alongside with the data. Because if you don't know where the data is coming from, right, like how can you trust this data? How can you even use it, right? We need to keep this information close by. So when you ingest the data, you can see the add data block was added describing that, okay, we got 1000 records into this data set. And what's important, if we run Canoe pull command again, so I'm going to run it actually on crypto compare dataset because it updates very frequently. It's going to check updates. It's going to reach out to the crypto compare API. It's going to check for updates. It will notice that some new data is present based on caching headers. It's going to get this data again, ingest it, but it will only add the data that hasn't been previously seen before. So if I run Canoe list again, now there's 78,930 records. Previously, it was 908. So we can see in the log for this data set here, that the last add data transaction added only 22 records. So in Canoe, we can see that the data itself is in the form of bitemporal ledger. So we remember the time, the outside world clock where this event happened, where this like data point was captured, but also we remember the system time when it got into the system. So this is our way to ensure the complete verifiability of source data. If you're a publisher publishing data in this format, any consumer of this data can ask you, okay, I had this data, you gave me this data last week. Can you confirm that this is the data you gave me? And it's all based on hashes, so you can verify the data even long after the fact when you got it. So this is something you don't get from JSON APIs, for example, because once you got the data from JSON API, like tomorrow this JSON API might not exist, right?
Yeah, no, I think it's fantastic. So then you run your own workflow engine, or does that happen on chain?
So our system right now is in a full peer-to-peer style collaboration. So like think of it as Git without GitHub. We're working on building out this layer that allows us to share data sets with one another in one in a one but decentralized place, so to say.
No, that's fantastic. I was just curious, like how you were doing it.
Yeah, I'm going to get into this in a minute when I'm explaining the pipelines. So now that we have two data sets, both of them are source data, we now can start processing the data. So I have prepared another couple of data sets. One of them is account balance data set. So you can see this is a second type of data set. It's a derivative data set. Derivative data set, unlike root, are not allowed to reach out to anything external. So they're only using data that is already in the system, already in the network. So this one is pretty simple. It just grabs the account transactions data set, and basically it just computes a cumulative sum of all the deltas in transactions of the Ethereum on this account, giving us at every point, at every transaction in time, a balance or the total balance of this account. The second data set is market value data set. And this one is much more interesting because it grabs two inputs. It grabs the balance and it also grabs the exchange prices data set. And this SQL is a bit more complex, but what it does is basically a temporal join of two data streams. So this is really cool stuff. So if I do Canoe add data sets balance USD. Oh, sorry. Market value. And I can do Canoe pool. No, I renamed the data set right before the demo. That was a mistake. So what it does now, it actually spawns the Canoe, Apache Flink engine, and is doing all these streaming transformations using Flink SQL. So we can actually switch back to the notebook, take a look at the transactions data set. I forgot to show you the contents of it. So it's pretty simple, just all the transactions. We can visualize the movement of Ethereum as a scatter plot. Once we're done ingesting account balance, we can visualize it as well. Yeah, as you can see, this account is very active, but it mostly just buys more and more Ethereum. And now that we're done ingesting the market value, visualizing this one as well. Yeah, so this is the end result. So this result, you can think of it as basically multiplying this event stream or time series data, multiplying it by this exchange rate, right? So what's interesting, we can jump into Canoe UI and talk about this a little more. So this is gonna spawn the web server serving our web frontend on top of your workspace. And we can explore the data in the same way we did through the command line, run some SQL. But most importantly, why I wanted to show you is this lineage graph, because it's really nice to look at your data like that. What we created here is not just a derivative data set, right? We created a pipeline that stays connected all together, and it's very easy to keep it up to date. So if I switch to another window here, and if I say Canoe pool account market value, it's going to immediately tell me that there is no updates, because two of these data sets that were inputs to this data set have not changed. But I can supply recursive flag. And what it's going to do is it's going to descend down the entire dependency chain, and it's going to start pulling these source data sets, checking for updates. It's going to notice that crypto compare data set was updated. It's going to ingest new data, and it's going to propagate all the updates through the pipeline. So it's very easy to keep these data sets up to date. So yeah, what we built here basically is a data pipeline, not just some disassociated data sets. And you can inspect the ledger of these derivative data sets and understand where the data is coming from and how it was achieved, because all of these SQL transformations are stored inside of that ledger. It's very important as well to mention that this SQL is a special type of SQL. Don't think of it as running like an SQL query inside of your database. All of these transformations are minimal and incremental because of the streaming nature. So you can actually, like these pipelines, we're designing them to achieve real-time speeds and operate on IoT scale volumes very efficiently, because they're only doing these micro delta updates to the end results. So once you have this pipeline, you can imagine, yeah, I forgot to say that this solution is super composable. So for example, in another window here, I have a different pipeline, and this is the one that you would build if you follow our demo. So you can see it can grow to a pretty complex pipelines. And every stage of such pipelines, like we did all of this on one laptop, but every stage could be created and operated by a different person and different organization, and shared with the world. So through Canoe push command, I'm not gonna do it, but I'm just gonna show you. With Canoe push command, you can easily share this data through some public S3 bucket, or even push it to IPFS. So we support one line push to IPFS plus IPNS key if you have the keys set up. But next thing I wanted to touch on is, once you see this data, like derivative data shared with you, it's really important. Once you get it locally, you will immediately start questioning, like, how can you be sure that you can trust this data? So this is why Canoe has went to great length on verifiability, reproducibility, and provenance. So I'm just gonna quickly show you the Canoe verify command. If you run Canoe verify on account market value, what this thing is going to do, it's going to scan the metadata ledger of this data set. It's going to understand what transformations have been run and when, and it's going to replay these transformations using the data from those data sets. So basically starting over, you can also supply the recursive flag, and it's going to start over from these data sets, run the transformations on account balance, then run the transformations on account market value, and produce the result. It's going to compare the hashes of this result and going to give you a yes or no answer whether you can trust this data. So it can easily detect any kind of tampering, basically through the reproducibility and deterministic nature of these transformations. So you kind of can think of it as us bringing the properties of the smart contracts directly to the SQL and directly to the enterprise big data engines.
And yeah, so everybody in the network basically can challenge the results of the like the data transformations.
Yeah, we're hoping that the network effect is going to be similar to like an open source software, right, where everyone constantly verifies each other's work. When you're using open source library, you don't immediately go and read the code. You trust that there was like security audit done by someone else because this library has like thousands of stars. So this kind of collaboration and network effect is what we're trying to achieve for these data pipelines as well. So this basically concludes my demo. I'm happy to jump to the questions. And yeah, to summarize, what we're trying to achieve is IoT data volumes, near real-time latencies, work seamlessly for on and off chain. Like I forgot to mention, but we're bringing the trust anchors to the publishers. And one of the biggest publishers can be the blockchains themselves. So the trust and data can be rooted in a blockchain directly, allowing you to easily query and merge data from both on and off-chain data sources. And yeah, enabling collaborative processing and getting verifiably trustworthy data.
Well done, guys. That is fantastic. I love the vision, and I love all the substance that you guys have already shown in the demo. I'll just pause in case anybody else has questions. I have a couple I'd love to dig in as well. One question for you, Sergey. Do you have any sense of how much hardware you'd like to see in each of these nodes that are processing with Kamu? Is it dependent on the workload, or is there a baseline that you want to see?
So yeah, hardware right now is an important question because we're using these beefy enterprise data engines like Spark and Flink. We're planning to migrate and support more streaming data engines that are Rust-based and require less hardware. But yeah, like for now, we want to achieve the state where we don't have to move data around. So for example, doing a streaming transformation on just one data set, we would submit a workload to let's say Filecoin VM that can actually spawn and run this engine for us, right? And do the transformations locally, co-located with the data itself. So you can imagine this pipeline that I showed, where the nodes and data processing would be co-located. So this is the state that we really want to achieve. And we're planning to integrate some Rust-based engines that can actually compile to WASM and execute on this type of nodes. But yeah, I think it's important to understand the value of the stream processing here. When I hear WASM, it immediately triggers a reaction that we just want to run some simplistic function on data. But if we want to have these continuously processing data pipelines that are resilient to all kinds of messy situations with data, imagine joining two data sets that are constantly out of sync of each other. There's a lot of edge cases like backfills, etc., that you need to account for. So it's really important not to ignore the history, decades of experience that went into these enterprise scale engines. So if we can manage to run them through WASM co-located with these nodes, I think it's going to be a pretty amazing state. Yeah.
I agree. Wonderful. All right. Well, if there's not any other questions, I'll highlight that we are going to include references to this in the meeting notes. So that'll be available on YouTube there for anybody else that wants to find more information. Thank you guys so much for sharing.
Yeah, feel free to try our demo and poke us on Slack. We'll be happy to answer more questions there.
Wonderful. Thank you guys. All right. So next up on the list is Al from Koii Network. Looking forward to learning a lot more about the platform. Al, I'll hand it over to you.
Great. Great presentation, guys. I don't have a demo today because the stuff that we're working on is pretty complicated, mostly for developers, so a little bit trickier to kind of give a full-on demo here. What I will show is sort of a little bit of background on why we're approaching the problem this way and what it is that we're really trying to accomplish with Koii. On the face, we have an attention economy, which attracts people to run nodes. Most of these nodes will be running on people's personal devices. So what we've started to work on is sort of a way of distributing compute operations onto many personal devices, and then wrapping those up into a stack that allows you to have sort of verifiability of a full web stack within this kind of very decentralized architecture. So we'll run through a few different ways that this helps, but just to kind of tie it into this computer over data working group, I want to talk a little bit about the 3 different ways that we've established, at least we look at from within Koii, as to how you can kind of have verifiable compute. So the first one, which most people are kind of familiar with in the blockchain space, is using a VM on a layer 1 chain. This is, EVM, FVM, any of the other layer 1 networks, and sort of the very deterministic structure of smart contracts that they have there. The second one, of course, is things that are more like fully verifiable compute, where you have internal proofs that are being generated as you verify things. And then, that would be like lurk and move. And then sort of what we're working on at Koii is kind of a little bit of a more flexible paradigm that is meant to complement these existing two options. And this is sort of a localized verifiable determinism, which is probably a very bad use of terms for this, but it's the best way that we've been able to represent it. And what this gets you is sort of this middle ground between the different capacities that you'd be looking for, and it makes it fairly flexible. So if you do want something with higher performance, you can tweak it for that. If you want something with higher verifiability, you can add more proofs. And if you're looking for something with greater privacy, you can kind of pull things that direction as well. So it lets you kind of tweak the knobs a little bit. So I'll go through a few different ways that we're tweaking these knobs, some examples of how we've done that. But first, I want to give a little bit of background about kind of how Koii actually works at a ground level. So these things called tasks that we have are basically designed to have an executable file that runs on some device, an audit that you write to verify that the executable was run properly and that nobody tried to mess with the outcome. And then you have basically a set of these nodes that we've been building up from our community, which have a reputation and collateral, which prevents them from misbehaving. And so if they get audited, then they lose some of their collateral and some of their reputation. And if they run the executable successfully, they get to earn a bounty in tokens. And we're working on actually broadening that just beyond the Koii token itself. So ideally, we'll have stable coins and other forms of incentives available as well. So this is a really quick overview of what this looks like. I'll just step through the points here. When you're a developer here, you deploy one of these tasks as an executable file. So you write, essentially a chunk of code. You deploy that out to a storage network like Filecoin or Arweave. And once it's up there, then you register that storage location to our kind of core master task contract, and you pay a bounty into it at that time. And then what happens is nodes come together and they look at these various bounties that are available, and they decide which tasks to run. And when they go to run the task, they stake some tokens, and then they start running this executable. In the process, though, they are also going to be witnessed by other nodes. And these witness nodes can basically look through all the payloads that are being submitted from these worker or service nodes. And the witness nodes are going to verify that everything's been done properly using that audit that we discussed. And so basically, you've got this kind of binary option here, where if there is a vote that's triggered and a bunch of the witness nodes see that there's something that needs to be audited, then the stake of the offending node can be slashed and they can be excluded from the prize pool. And also their data is then discounted as malicious. And so we don't use that data anymore. And so this is really useful for things like web scraping, for things like downsizing thumbnail images. We'll go through a bunch more examples for that. So before we get into that, I want to talk a little bit about gradual consensus, which is the way that we've set this up so far. And I guess execution environment first. So within this task execution environment, you have a couple of different features that make it really useful for building these sort of consensus games, is what we kind of call them. So the first thing you get is this JavaScript VM. We're working on having these for Python and hopefully Go. You can currently kind of use them in Rust if you wanted to, because you can compile down to WASM and you can put that in there. You get a full support for all the existing NPM modules, which makes it really easy to build in things like proofs, because there's a lot of verifiable random numbers out there that you can just pull in a proof library for that, and then you can use it inside your task. And so you get to have a lot more flexibility and composability, and you don't necessarily have to build everything yourself. You also get to have a file system on the node, and these are all namespaced. So the file system that you get is basically like a little folder that's just for your task. And this is going to run on the device that is running the task. So each device might have its own copy of each set of files, which can mean that you can have sort of competing versions of truth. And then when they come together, you get to compare those competing versions and hand out rewards. So what you might have here as well is you might have a need for something that's a little faster than a file system. So we install the Redis cache as kind of part of this. You also get REST API built into it. We chose REST API for this because then you can put it behind caching, and it makes it a lot easier to start distributing that information without having a lot of load on these end nodes. And you also get some prompt timers in case you have recurring operations that need to happen over time. Finally, you also get two types of secrets. Basically, you get secret injection, which is kind of where you can ask the node operator to configure something like an API key, and then inject that API key into the task execution. And so you can get your node operators to all go and get free tier API key for something that they need to fetch, maybe price data, maybe go and get some kind of like a Infura key or something like that. And that means that these nodes can actually act like a full-fledged server because they're going to each have their own set of private keys, or secret keys, I should say. And then in addition to that, obviously, you also get some private keys for signing things. We've been working on making this sort of distance from the node operator themselves. So the way this will work, based on kind of the latest iterations that we have, is that you will be able to establish your kind of core key, and then you can have secondary keys that are backed by that core key. And so as a node operator, you're signing every payload, but you're not exposing your personal keys into the task environment. You're actually generating a new set of keys for each task. And so a couple of caveats of this would be, I mentioned that we're looking at trying to extend the task environment a little bit so that you can do things like Python and Go, Rust, kind of via WASM, but eventually we'd like to have that be a little bit more robust. And then for the keys, you get an ECDSA key for Ethereum, you get Arweave keys, which are RSA. We also have Solana keys because our kind of core settlement layer is a fork of Solana. And we've been working more closely now with Near and Filecoin, so we're going to be establishing those keys as well in the near future. So the idea here is to put together kind of a set of tools that will make it extremely easy for any developer who's familiar with kind of basic programming languages to create consensus games that can be played by these various nodes in the network. And the point of this is that then once you have a consensus game and you have a bounty and you have an audit, you can get a bunch of nodes to coordinate their efforts, and you can get them to accomplish some kind of seemingly not possible to decentralize task. And the neat thing here as well is if you are having a hard time coming up with audits for your system, and you just wanted to run this, say you have like a mobile app, you can run it across all the devices that are part of your mobile app network. And you can potentially even find a way of permissioning access to it. So you could say, maybe there's some sort of an OAuth hook that has to happen when somebody creates an account. You put them through a reCAPTCHA, and then they can become a node operator, but only in like a very permissioned sense. So that, your specific task might have its specific subgroup of nodes. So we're really trying to more establish a design pattern than to provide like a one-size-fits-all network. So to give a little idea of how this gradual consensus thing works, it probably helps to understand proof of history and how Solana operates. So we actually recently forked the Solana kind of core chain. We're not really trying to compete with Solana on what they're doing. They're very DeFi focused. They've got a lot of NFT type stuff that they're doing. Really, our goal has been mainly to create sort of a central heartbeat that can act as a kind of a cadence for all of these different consensus games that are happening. And so with Solana, you have epochs. Solana epochs can take 2 to 3 days usually. Ours happen twice a day, actually, so they're every 12 hours. And what this lets you do is you can establish sort of periods of your game. And so your first epoch of the day is kind of the creation epoch. That's when your nodes are actually going to go and do their job. And then the second epoch is when they're going to verify the results of the previous thing that happened. And so if you set this up properly, you can have a distribution of rewards that happens once a day, and it verifies some kind of complex behavior that has to be ongoing. And you might be thinking, well, what happens if I want something to happen in the afternoon? That would be a huge problem, right? But the neat thing about this is that these various epochs actually layer on top of each other. And so your first epoch can actually be happening while the other epoch is happening, because your nodes that are part of this group will be, in the process of being audited. And if their stake is slashed before the end of that epoch, then they're not going to be able to submit their results to the system. And so you're still actually just as secure, but you're basically able to layer these things kind of in sequence so that you can have consistent uptime of your service that you're trying to run without having to try and wait for the verifiability. The advantage of this, though, of course, is that we're slowing down the whole consensus game a little bit. And so we're not trying to provide something that's instantaneous. We're not trying to provide something that is going to always work exactly as expected. We're mostly trying to prune the group of nodes to find nodes that are always going to be performing reliably, and then give those a higher reputation so that they can be included in more tasks. And so to bootstrap the network, we actually have basically offered a kind of a pre-sale to people that will be running nodes over the initial period of the network. We've got about 120 of these kind of pre-sale nodes that have joined, and they've all purchased tokens so that they're kind of invested in making the network successful. And then from there, we'll be opening up to the community, which we now have like almost 45,000 devices RSVP'd. And so the idea here is that over time, we can start to build up this group of people that we know we can reliably trust to run sort of Kubernetes style operations across their devices. And then if anybody does get, for example, corrupted, we can exclude that data fairly efficiently from the pool. And so this is mainly meant as a design architecture. We're working on establishing it in a variety of different places. So I'll go through a few of those now and kind of give an idea of how this can be used. And I guess the one thing to think about this as well as we talk about these different applications is that the idea is that each individual task is going to solve one problem at a time. You could try to use these as web servers as well if you wanted to. So you could have sort of like a wider, super app that would run as a single task. The problem with doing it that way is that then you have more moving parts that can break, and it becomes harder to audit. And so ideally what you do is you actually break down your task into multiple kind of more deterministic sections, and then you audit each of them in a separate way. And you can even have them run on potentially separate nodes, which is really cool. And so if we imagine like kind of the original use case of Koii was web scraping. And so if you wanted to be able to scrape the internet, index the data, and then search that data or filter it, you would not actually want that all to happen in one task. You'd want it to happen in multiple separate tasks. And then ideally all the data gets stored into an IPFS style cluster, and it's all accessible to people throughout this entire process. Or you can query some of the nodes, which will have the REST API available, and all the data would exist there, which is how we've kind of been doing it so far. So the interesting thing about this, though, is that the second group here, which is the one indexing data, is going to be able to fetch over the REST API all of the web scraping data from the original group of nodes. And then they can add kind of metadata to it, index it, provide kind of a more deep and meaningful set of data. At which point, then you can add an additional layer that does search and filtering on top of that data set. And so as you kind of begin to break down these problems, you realize that each of these individual small tasks becomes somewhat verifiable. And the idea here is to kind of demonstrate that you can do this for almost any compute operation that you would need to do. As long as you can break it down into more and more steps, you can make it more verifiable and more trustless. And you can also include more parties, which means you can kind of distribute more tokens to more people, get them more involved in your community or whatever you're trying to build. And you can kind of have that extra layer of trust as well. And so you get around some of the efficiency issues by also sort of including more folks in the process, and then you will make it more trustless by adding more and more audits to the system. So yeah, some examples. So proofs are one way that you can do this. So I mentioned verifiable random numbers before. That's one thing. So those have been around for a little while. They're possible to spoof if you have enough compute capacity, but if you have enough people doing this verifiable random number process, you can layer upon it some kind of averaging thing or some kind of a way of using that randomness to create more randomness. And similarly, you can also use this for attention tracking, which is how we've been doing this. And so with our attention tracking game, you have basically end users submitting proofs of real traffic on the website that they're viewing, which effectively are just signatures. But they're all verifiable. And so if you have enough of these verifiable signatures coming together, you can create something that is verifiable on a macro scale as well as on a micro scale. And so another tool that's kind of in the tool belt here is deterministic actions. So we've been using this for things like transformations. So if you want to take a thumbnail and size it down, you can do that. And you can also use these kind of deterministic actions to do things like indexing, because if your index comes out to a specific pattern, it's fairly reliable to go over that same data set on another device and verify that the index is generated the same way, assuming that you have access to the same data set. Again, though, this is why you kind of need to break down these problems into smaller and smaller pieces, because if the data set is too large and it's not all in the same location, then the index might be different. So it's really about trying to break down these tasks to make sure that each individual task is verifiable. And from there, there's also kind of the one last one, which is sort of I think probably a unique component of the Koii network, which is that you can do time-based verifications of sorts. And so this is another side effect of having this Solana fork at the core of our network kind of acting like a heartbeat. And so you can use sort of timestamping the same way that a traditional web server does, where you can verify that a payload that was submitted has a correct timestamp from a correct epoch within our system. And actually within each epoch, they're actually also broken into these slots, which each have a unique hash to them. And so as long as each of your things is actually timestamped properly, you can do things like retrieval markets, and you can make sure that nodes are giving no preferential treatment. Because if the retrieval requests are all posted to the node's API, then you can see that they're actually coming in with proper timestamps. And if an end user submits a request and they don't get back a response from the server, they can submit that same request to another server or another node, we call them. And then that node is able to serve that request as well. Similarly, this also works really well for the web scraping use case, just as a side effect of the fact that some content changes quite regularly. So if you know where the node is in the world and you know what time they actually queried that server, then you can actually create a proof that verifies that they have a valid result from that particular website, which is very different from how you do this in the traditional sense, because traditional web scraping and proxies, it would actually be very hard to tell if you were getting a spoofed result. Most of the time, you kind of rely on proxy botnets to do this, and they don't seem to do that very well. And so there's a lot of these different kind of components. This is kind of the cookbook that we've been working with so far. We're in the process also of exploring a lot more types of proofs that you can put in here. There's a lot of other deterministic actions that have kind of been coming to the front. We've got even some people at this point working on ways to verify audio files that match each other. So, extracting like a standardized snap from a piece of audio and then verifying that it matches a specific master file, kind of like a Shazam type behavior. So there's lots of different flexibility to this. It really opens the doors for developers. But if anybody has any kind of interesting applications that they'd like to explore, we're really open to trying to help you go through those and helping you find the right, the right structure of proofs, deterministic actions, and potentially like timestamps to make that possible. And so I guess the last thing would be that there are always the possibility of having all three of these components or even more as kind of a combo. So if you have something like search and you want that to run in a reliable, decentralized way, then you can combine a lot of these different factors to ensure that your service quality is consistent across all the nodes that are providing it. And of course, these are not solved problems. What we're creating here is not a general solution. It's more of a sandbox that allows you to try things out and build these consensus games. So just kind of a little bit of a deeper example with these proofs. Verifiable random numbers are really designed to give you the ability to generate a random number and then prove that there is randomness within it. And this is something that like immediately when we started talking about this kind of an application, people looked at it and they said, well, what do you do if somebody makes a task that says generate a random number for me? It just happens to turn out that that's something that you can do quite easily. And so this exact example is one of the main reasons that we kind of stumbled in the beginning here. And then we realized that these kind of generic proofs that you can generate, they seem to support a lot of different types of behavior. And so there's actually a lot of people who've worked on this across the whole blockchain ecosystem, because generally speaking, almost every type of oracle needs to have a proof now. And usually when you go to set up an oracle, you end up writing that proof as a library or you use someone else's, and there's usually some record of that somewhere. And so for a developer who's trying to set up their own network that's going to do something specific, this is actually a kind of a boom to these people. So we've gone out kind of with crypto and we've sort of incentivized people to create all these proof libraries and distribute them more or less for free. So they're all out there and you can pretty much jump into them. I mentioned the attention tracking before. That's kind of a good example of a signature type proof. And so one of the main things that we have with Koii is this ability to create these multi-wallets that have all kinds of different wallets within them. And so if you wanted somebody to generate a signature and their wallet is attached to an account that has some reputation in the system, it becomes fairly unlikely that somebody who has that reputation is going to also forge a proof or to contribute forged proofs to somebody else's account. And so a lot of these different kinds of signature type things can be really beneficial in order to create kind of layers of trustlessness and to add additional trustlessness to these systems. And I guess the last one on this one is whenever you have REST APIs or the voting that's happening behind the scenes in gradual consensus, all of that is also going to be signed. And so as a part of having these REST APIs, whenever a REST API on one of these nodes distributes information to you, it's going to sign it. And it's going to say, this is my data that I'm standing behind. And so if it turns out that there's anything in there that's incorrect, then that node is now accountable. And you can build that into your audit function as well. And then similarly, of course, the voting process that happens to release rewards or to audit people is also all signature based. So you have a lot of this data that's getting generated and it kind of creates a sort of an auditable trail that's behind all of this consensus process. And so deterministic actions, I mentioned a couple of them. Transformations like generating thumbnails are really good. And so if you have something like, if you've got like a 5 megabyte image, you don't want that to be in a list view on a social media website because it's going to bog down everybody in the process. It's going to make it basically useless on mobile. And so what you can do though is you can run a hash function against it. You can hash the original image, you get a hash from that. You can compress the image and you can do a fairly deterministic compression and you get a smaller hash. Or well, you don't get a smaller hash, but you get a hash with a smaller file. And now we know that that is the correct thumbnail for that image. And a lot of these processes can be established to run pretty effectively on most hardware. So depending on what the environment is, you can usually pretty much rely on that to output reliable results. Of course, these have to be tested depending on the application. But you can pay a few Koii tokens, run a test across multiple nodes, and make sure that it's going to work on lots of different hardware specs. We are also working on kind of some tools to index all the different hardware that we're running on the network. So we're just in the process of onboarding nodes now. But we're hoping to also have sort of a list of, what sort of operating system they're running, what sort of hardware specs they have, all those sort of parameters that you would need to use to calibrate this kind of data. So that's hash comparisons in a nutshell. And I guess there's sort of a question of performance trade-offs here, where you obviously don't want like most of the nodes in the network to spend their time compressing the same image file. And so what you can do to avoid that is you can set up your audit in such a way that the audit can be triggered by one node, and then have a bunch of other nodes jump in to support that audit. And so if one node has a fairly high reputation, other nodes might choose to support that audit without actually running the same tests themselves. And so you don't actually need everyone to go through and audit every single thing that happens. You sort of need more of a random sampling, or sort of like a fisherman style test. And this can be really, really effective as a way of reducing the amount of duplication of the work, so that you can get the same performance without having to have like an overwhelming amount of compute that's just happening on all these devices. Most of these devices are consumer hardware, so they're basically free for all intents and purposes. Most people aren't that worried if their computer is doing these things while they're sleeping. They don't mind if they're doing a bunch of extra compute. They're pretty happy to just get paid for having the hardware and the internet connection. But if they, if you do as an operator want to be a little bit more eco-conscious and reduce your energy output, this is a really good way to do that as well. You can kind of choose how much verifiability you want and how you're going to actually execute on that. And I guess the final point here is that this also supports some interesting privacy attributes, because depending on how your proofs are generated and what you're trying to do, you can implement some zero knowledge proofs and things like that would allow you to actually integrate significant amounts of privacy into the structure. So I'll mention the time-based verification thing one more time, just because it's kind of fun. This means that effectively with the K2 Solana fork, you can get these slot numbers all the time. And so with traditional like client server architecture, if you're submitting a payload to a server and the payload is too old, or there's something happening where the server doesn't want it because of the timestamp, you can have certain kind of protocols for requesting another payload. And I think the exact same thing should be applied here for the most part. So if we're talking about these types of like Oracle nodes that are going to be here, most of the time, these Oracle nodes will need to accept a lot of different payloads from all sorts of different people. Web scraping as an example again. You need to know when the page was scraped, because at the time that the page was scraped varies too significantly between the data. It's very hard to have consensus about the data that's being outputted. Whereas if you have a significant number of timestamps for all these different points, and the node that's accepting the payload sees the same epoch or the same slot as the node that's submitting the payload, then they can both actually tell that it is the correct one. And since these are generated basically every couple of seconds, it provides a very small window to have that data come out of that website for the specific locality where the node that's scraping the data is located. Sorry if that's a big mouthful. We've been working on a lot of this stuff for a while, so we're working on kind of condensing it down to make it make a little bit more sense, but hopefully this is somewhat educational. And I guess beyond just the web scraping market, there's also a lot of use for this in terms of retrieval. So if you're trying to fetch some data off of IPFS or something like that, being able to timestamp your initial request and then being able to timestamp the data that you get back when it comes back is also really helpful, because then you can kind of tell if the retrieval nodes are doing their jobs properly, especially if there's some kind of a relayer in the middle. So if you have one node that receives the request and then it passes it up to another set of nodes that are going to retrieve it from the system, that's going to allow you to basically verify that the nodes that are actually retrieving the data are doing so in an efficient fashion, and you can start to benchmark them against each other. And then I mentioned the data gathering and web scraping side of this as well. So some options there. So again, just to recap this cookbook, you've got proofs, verifiable actions, and timestamps. And then on the other side, you can also use kind of APIs between the nodes to take some shortcuts here. So you can get the nodes to host something onto their API that's going to have some proof data associated with it. You can also use storage layers instead of blockchains, which makes a lot of this stuff a lot more efficient. If it's on IPFS, it's going to be significantly easier to index it and retrieve it. And it's going to mean that you're not trying to pay some absurd gas fees to upload something. You can also get your nodes to act as IPFS pins as a part of their task, so they can temporarily hold on to something and then pass it off to a Filecoin miner to hold on to it for a longer term. And I would say generally try to use witnesses and audits, not always consensus, because that's going to reduce your performance issues a little bit, because you're not actually always worried about having a perfect consensus. You're mostly worried about auditing things that are going wrong or being used incorrectly. And that kind of leads to the last point, which is that speed of results is not speed of verification. And so with most of these systems, you can kind of have an optimistic approach to this, because you know that the nodes that are participating in your task are probably going to consistently have the same behavior. So this is kind of similar to Uber or Airbnb, where they're actually trusting that the person who runs the Airbnb is going to consistently be a sane person and not change their behavior too erratically. or an Uber driver, for example, who has previously never been a drunk driver or has never been in a car accident while driving, is unlikely to have a car accident while they're driving with a passenger. And the same is probably true of these node operators for the most part. They're going to be fairly unsophisticated, operators. And so as a result, they're mostly going to press the button and play the task. And if they're consistently doing that, then it's very unlikely that they're ever going to run a malicious script. And so over a long enough time period, you can actually build up a significant group of these trusted people who you can effectively just guarantee are going to run the task as you requested that they will. And so again, this is not necessarily for kind of the sort of stuff that people are doing very close to the Filecoin storage. We're not trying to do massive data processing here, but it's really effective for things that happen at kind of the web application layer. And so this year, or last year rather, in about an 8-month pilot, we got about 30 million views on the network. That led to about 300,000 tokens being minted. And now we have about 45,000 consumer devices between phones and computers that are now RSVP'd to be part of this network. That number goes up just about every day. And so we've been gradually just kind of building up this attention economy as a way to bring in all these people to give you all kinds of compute capacity. We have lots of grants available in Koii tokens as well, if you'd like to try deploying some tasks onto the network. We're actually just about to start onboarding these nodes. So we could use any crazy ideas that people have that they want to use our sort of honest botnet for. So please help yourselves. So yeah, thank you all for your attention. If you have any follow-up questions, you can join me on Twitter, or you can join our Koii Discord at discord.gg/Koii. We also have the docs portal and blog link here where there's a little bit more information about how all these things work. Thanks.
Excellent. Thank you so much, Al. That was tremendous. And I'm just following along with you there. For folks that want to get involved and they want to deploy use cases onto the Koii network, is there an easiest path in terms of, you talked a lot about the witness approach and verification. If I just have some web server that I want to have running arbitrarily, does that require any amount of verification, or is it manual, or what do you recommend?
So when you deploy the task, you're going to write the task itself, and then you're also going to write an audit. We're working on creating kind of a cookbook for these audits. So a lot of standard operations that you would have on a web server, we'll try to give you examples of how to do all of those in our tutorials. And we're really hoping that we can get to the point where this is composable. So if you say, I want to have an endpoint that does X, we'll say, well, that's how you audit X, and just try this audit script that's already written. So it should hopefully be pretty plug and play within a few months.
Brilliant. All right. Thank you so much, Al. That was tremendous. Lovely. Dan, I'll pause in case you guys have any questions, and if not, we can wrap up.
Yeah, I have one. I'm curious about the layering of the tasks, like you mentioned, web scraping and then indexing. When you run first layer, do you have to wait for the task to settle fully, like all the audits and verification pass? Does it basically mean that there's a 12-hour settlement window between the layers, or you can kick off the next layer of tasks and have them all undone if the data proves to be non-reproducible and verifiable?
So there's a few ways to look at that one. The thing that would happen there, you could wait 12 hours to make sure that everything's been fully audited. But you could also have sort of an optimistic approach to it, where you say, I know that this node operator has been consistently operating the task for a year and a half, and they have a really significant stake. They have a very high reputation for their node operation skills. And at that point, you can kind of trust those results ahead of time. And so if you wanted to, your indexing task is going to be depending for its success. Each of the indexing nodes are competing for that reward, and they're also trying not to get audited. And so if they wanted to, they could shortcut that by getting the results from one of the nodes that they already trust, using that to compute their result, and then they're ahead of the curve and they get to submit their result first. And so there's a few ways to kind of build in layers of accountability here. But yeah, you're right. If you don't do that, then you have a little bit more of a delay. So there's two ways to balance it. You can get the results faster, or you can have higher levels of verification. I think it depends on what you're trying to do. So if it's a search type application, maybe your nodes are going to be providing slightly different search results. But the nodes that are providing the wrong search results will eventually get audited and excluded from the pool. And so you're trying to mostly build up that group of trusted nodes over time.
Mm-hmm. Yeah, I guess if there's a way on the layer 2 to detect that, okay, this part of the data will actually proven to be non-trustworthy, and we can undo this, like unincorporate it from the overall data set, that would be pretty interesting.
Yeah, and I think that will happen fairly organically, because as a node loses its stake or is audited, then it immediately is cut out of the pool. And so it would no longer be shown as, like, its IP address wouldn't be shown as one of the nodes operating the task, for example. And so it wouldn't be queried by the nodes that are part of that task. And actually, I guess one of the other sides of this is that you can run an audit at any point. And so if a node is broadcasting something that's on their API, they can get audited even during that first epoch, because that would technically be part of the previous audit period. And they might get locked out, within 3 hours instead of within 12. So it can happen on a much shorter time span if you get enough confirmations.
I see. Very interesting. Thank you.
For sure.
All right, I think we can go ahead and wrap for today. To the Koii Network team and the Kamu Network team, thank you guys so much for presenting. That was excellent content. We're going to post this up on the YouTube page soon, and hopefully we'll get some feedback from the community.
Lovely. Thanks for having us.
Thank you, Wes.
Thanks, everyone. Bye-bye.
Take care.
Bye-bye.